In the previous video, I provided an overview of media access control protocols. In this video, we are going to cover a very simple random access protocol called Aloha. What does Aloha stand for? It's actually not an acronym. It is a word for greeting in Hawaiian language. Now, where did this Hawaii come from? In 1970s, a first packet radio network was deployed at University of Hawaii to interconnect the Hawaiian Islands. And the protocol they used to resolve contention across these stations in the different islands was the Aloha MAC protocol. As such, this protocol never made it into any products or standards, but it has been an inspiration to many operational products as well as standards like Ethernet, Wi-Fi, even cellular. Earlier I mentioned that the cellular architectures employ TDMA in combination with FDM. So they do that, but prior to allocating a TDMA slot, the coordination happens through random access channels, and this is where something similar to Aloha is employed. Now, why should we study such a protocol that is no longer in use? This reminds me of a quote from Mallory. So he was asked, why do you want to climb Mount Everest? And his famous answer was because it is there. We are not covering this just because it is there. I like to cover this mainly to demonstrate how these protocols are analyzed theoretically. And this can be a very useful tool. Implementation as well as simulations can take a lot of time, but if you make the right kind of assumptions, you can quickly analyze to get a rough idea of how a protocol performs. And based on that, you can tweak the protocol before actual implementation or simulation. Now, many of the media access protocols are very complex and analyzing them is often very involved. So Aloha is one such protocol which is very simple and relatively easy to analyze. So you can get a good idea of how analysis is done for protocols. So here is the actual protocol. This protocol I'm going to call Pure Aloha. There is another protocol called Slotted Aloha which we will cover shortly. As mentioned, the protocol is very simple. All the sender does is whenever it has a packet, it just sends the packet. One thing that is feasible in this setting is that the sender can determine the status of a packet at the end of transmission. By status, I mean whether the packet is intact, in other words, it reached the receiver fine, or it underwent a collision. So how do you detect whether a packet was intact or it suffered a collision? Typically on a wire, what the sender does is when it is sending the packet, it also taps into the wire to figure out what is being sent on the wire. So it receives what is being sent and then does a comparison between the both. If they match, that means things are fine. But if they don't match because the signal is getting garbled on the wire because of another transmission, it will conclude that there is a collision. Now in Pure Aloha, if it detected such a collision, all the sender does is it waits a random amount of time and tries again. So for example here, it came, it sent, there was no collision, some other packet came, it got sent. Here when it sent a packet, another packet came and they both collided. So this is a collision that is being represented like this. Then after some time, let's say this is the collided packet, after some time it is again going to retransmit the packet and this time is random. As you can see, this is a very simple protocol. Now, what do we want to analyze about this protocol? One very useful metric is the efficiency. Basically, to calculate efficiency, you need to answer the question, what is the probability that a transmitted frame does not suffer collision? If you know this probability, then you can calculate efficiency of the protocol. So if this probability is high, in other words, the chances of success are very high, then that protocol is a very good protocol in terms of efficiency. If this is low, then it is not a very efficient protocol because packets keep on suffering collisions with high probability. Before I get into the analysis, one point I wish to make is that there is a lot of detail behind this, behind the analysis. So I'm not going to cover it in depth. but I'm going to provide all the necessary detail for you to understand the analysis at a high level. So that would suffice for this particular course. So one assumption we are making is that the frames that the sender transmits are all of equal length. The second assumption is that the probability of k transmission attempts per frame time, in other words, if you look at a frame time, this is the frame time, the number of attempts that are made to transmit in this duration, both old transmissions, in other words, this refers to retries because your previous transmission underwent a collision, or new arrivals. All these attempts, this probability of these attempts follows a Poisson distribution with mean g per frame time. In other words, the probability that there are k attempts during this time is given by this particular formula, where g is the mean number of attempts per frame time. If you don't know about Poisson distribution, I would suggest that you quickly refresh what it is through the internet. To get to this assumption itself, there is an underlying assumption that there is an infinite user population generating new frames with a Poisson distribution, again with the mean rate less than 1 per frame. What will happen if the arrival rate, that of new packets, exceeds 1 per frame? That's right, the system will become overloaded. Your incoming rate is going to exceed your outgoing rate. That leads to an unstable system. So what's happening here? Basically, there are infinite users generating new arrivals with a Poisson distribution of rate less than 1. And now as part of this protocol, they are going to attempt transmission. Some will suffer collision, some are new attempts. This overall old retransmissions as well as new arrivals combined, the number of attempts you are making per frame time is also Poisson with this particular rate. This g that is here is a variable that is kind of given to you. Suppose in a frame time, so this is the frame time, the number of attempts, as I mentioned earlier, this number of attempts, whatever this thing, has a mean rate of g. For example, if g were 0.5, by the way, that's not being represented in this figure, what this is telling is one attempt is being made every 2 frame times. Now when you have a g like this, and once a frame comes, the probability that a frame is successful is given by this PS term, then the throughput of the system is given by this particular formula. Suppose if PS were also 0.5, then the throughput is 0.5 into 0.5, which is equal to 0.25. So what this means is, in the long run, in a frame time, you're only able to get out 1/4 of a frame. So in order to calculate this throughput, as I said, G is kind of given, we need to determine PS. So how do you determine PS? Under what conditions will a frame not suffer collision? So recollect the Aloha protocol. Basically, a sender sends whenever it has a packet to send. And if there is a collision, it waits for a random amount of time and tries to send it back again. Now, if this is the protocol, under what conditions will a frame not suffer collision? So think about it, it's not that difficult. So here is a graphical representation of this. So here is the frame that is of interest to us. So this is the frame we are interested in, which starts at T0, and this is the frame time. It goes on from T0 to T0 plus T. So I claim that this frame will suffer a collision if any packet transmission happens within this period, which is the vulnerable period. So if packet transmission starts somewhere here, it is kind of going to overlap with this particular frame. And similarly, if packet transmission starts anywhere in this interval also, it is going to overlap with this particular frame. So as you can see, the vulnerability period here is twice the frame time. So with this in mind, let's look at the analysis. So let's look at the transmission attempts that are being made on the channel. So that is being represented by these arrows. By the way, these attempts can be old packets being retransmitted or new arrivals. And I'm using this notation Ti to represent the time interval between the ith and the ith plus 1th transmission attempt. So this is T1 between the first attempt and the second attempt. T2 is between the second attempt and the third attempt, and so on and so forth. So this is the crux of the analysis, where I claim that the ith attempt will be successful if both Ti and Ti minus 1 exceed a frame time. So for example, this attempt was successful because the previous transmission T1 exceeded the frame duration. If it didn't, if this was really short, this frame would overlap with this particular frame. So that is where Ti minus 1 has exceeded a frame duration. Not only that, this frame was successful because the next arrival did not happen within the frame time. In other words, the next arrival did not collide with this. It turns out that these intervals are independent just because the nodes, whenever they have a packet to send, they are not taking into account anything that is happening on the channel. They just transmit. Thereby, these intervals are independent. Now, the probability of success is basically the probability that Ti minus 1 exceeds the frame time times the probability that Ti also exceeds the frame time. So this is the probability that an attempt will succeed. When you have Poisson distribution, it turns out that the inter-arrival time between attempts is exponentially distributed. If you have read up on Poisson distribution, this will definitely be mentioned. So basically this probability is given by this. What is the logic for this? Suppose you have an arrival, for your other arrival to exceed this time is basically within this interval, no other arrivals have to happen. In other words, within this frame time, you don't want any other arrivals to happen. If that were to happen, then this inter-arrival time is going to exceed the frame time. And the probability that no arrivals is basically the probability that k is equal to 0. Substitute in there, you're going to get this particular probability. And since we are looking at this and both are independent, that is why it is a product, and each have this particular probability e to power of minus g as well as e to power of minus g. So the probability of success turns out to be e to power of minus 2g, and the throughput, which is given by g times ps, turns out to be this. Now s is a function of g, and the maximum value that s will take turns out to be when g is 0.5, and this maximum value is given by 0.184. So in the long run, in a frame time, you are only able to get out 18% of the frame. So this is the same thing represented pictorially. So we are dealing with pure Aloha, so focus on this particular graph. So s varies with g in this particular fashion, and it peaks when g is 0.5. And the value it has at this point is that 0.18. The probability of success here turns out to be 37%, but the throughput is still only 18% because this happens when g is 0.5. In other words, one attempt is made every 2 frame times. So when load becomes high, in fact, the throughput is tending to 0, and even when the load is less, the throughput is not much. So this performance is rather dismal. So why do you think the performance is so poor? The reason Aloha does bad is because in this protocol, a user, when it has a packet to send, transmits it right away without care or concern of what is happening in the channel. For example, if there is an ongoing transmission and a packet comes, this user is just going to start transmission right away, and this is going to result in a collision. So what we will see next is a variant of Aloha called slotted Aloha that improves this behavior.